To understand why this single point of light matters so much, you first need to understand exactly what Alpha Centauri actually is, because it isn't one star, it's three. Alpha Centauri A and Alpha Centauri B are a pair of Sun-like stars, locked in a long looping orbit around each other, and a third, much smaller and dimmer red dwarf star, Proxima Centauri, sits much farther out, orbiting the pair from a huge distance. All three stars sit at just over 4 light years away, meaning light itself, the fastest thing in the entire universe, takes over 4 years just to cross the gap between their system and ours. In the language of the cosmos, where distances between stars are more typically measured in tens or hundreds of light years, 4 is essentially next door. This is, quite literally, the closest neighborhood to our own solar system anywhere in the observable universe. And it's why astronomers have spent decades pointing every instrument they could get their hands on directly at it, hoping to find exactly what Webb may have just found. Astronomers already knew this neighborhood wasn't entirely without planets. Proxima Centauri, the small red dwarf sitting farther out in the system, is already known to host 3 confirmed exoplanets of its own. But Alpha Centauri A and Alpha Centauri B, the 2 sun-like stars that make up the heart of this system, the 2 stars closest in character to our own sun, had never revealed a single confirmed world, despite being far more interesting targets for a very specific reason. A planet orbiting a genuinely sun-like star, sitting in that star's habitable zone, is exactly the kind of environment astronomers dream about when they imagine finding another world, even remotely similar to our own. If Webb really has found something real around Alpha Centauri A, it would represent the closest such planet ever discovered anywhere in the galaxy. Here's where the story gets its real weight, the detail that turned a faint infrared dot into one of the most talked about results in exoplanet science this year. This wasn't actually the first time this exact object had shown up in the data. Astronomer Kevin Wagner, now an assistant research professor at the University of Arizona's Steward Observatory, first spotted hints of a possible planet around this system all the way back in 2019 using an entirely different telescope, the Very Large Telescope, operated by the European Southern Observatory in Chile. That initial 2019 detection was faint, uncertain, and easy to dismiss as noise or an instrumental artifact, exactly the kind of shaky signal that shows up constantly in this line of work and usually turns out to be nothing. But then, 5 years later, in 2024, Webb's MIRI instrument, an entirely different telescope using an entirely different observing technique, picked up a bright point of light sitting in almost the same region of the system. 2 separate instruments, 5 years apart, both hinting at the same object in roughly the same place. That's the kind of coincidence that makes astronomers sit up and take real notice, rather than filing another blip away as noise. And yet, even with 2 separate detections backing each other up, the scientists involved have been remarkably careful not to oversell what they've actually found. And that caution itself tells you something important about how seriously they're treating this. As Charles Bachman, one of the lead researchers on the Webb observations, put it, if this really is the same object showing up consistently across both the 2019 and 2024 observations, this would become what he called a touchstone object for exoplanet science, a genuine benchmark world that telescopes could return to again and again for detailed study, precisely because of how close and how bright it would be compared to almost every other exoplanet ever found. But that word "on if" is doing enormous work in that sentence, and it's worth sitting with, honestly, rather than glossing over. Astronomers still don't know for certain that they're looking at a real planet at all. Here's why that uncertainty exists, and it's a genuinely fascinating problem. Once you understand how difficult this kind of detection actually is, trying to directly photograph a planet orbiting another star is a little like trying to spot a single firefly hovering directly next to a lighthouse beam from many miles away in the dark. The star itself is almost unimaginably brighter than any planet orbiting it, and any faint planetary light gets almost completely drowned out unless you use extremely sophisticated techniques to block the star's glare, without also blocking out the planet sitting right next to it. Webb's coronagraph does exactly that, physically masking out Alpha Centauri A's overwhelming light so that only the comparatively faint material around it remains visible. But that process is delicate, prone to leftover artifacts, like stray light and subtle instrumental quirks that can sometimes mimic the appearance of a real object where none actually exists. Astronomers have already cataloged nearly 6,000 confirmed exoplanets across the galaxy. And for every single one of those confirmed worlds, there are countless additional candidate detections that turned out to be nothing more than statistical noise, dust, or optical artifacts once follow-up observations came in. That's precisely why the team behind this discovery has been so deliberately cautious in how they've described it, refusing to call it a confirmed planet even now. The object detected around Alpha Centauri A is being described specifically as a candidate, a strong, tantalizing, scientifically serious candidate, but a candidate nonetheless. Exactly the kind of hedge scientists use when a result is exciting enough to take seriously, but not yet solid enough to bet a career on. What makes this particular candidate different from the sea of other unconfirmed blips scattered throughout exoplanet research is the strength of the specific evidence stacked up behind it. 2 independent detections, using 2 completely different telescopes, separated by 5 years, both pointing to roughly the same location around the same star. If this candidate does turn out to be real, the physical picture astronomers have pieced together is genuinely remarkable. Based on the brightness and infrared signature picked up by Webb's MIRI instrument, researchers estimate the object is a gas giant, roughly comparable in mass to Saturn, orbiting Alpha Centauri A at a distance of about twice the gap between the Earth and our own Sun. That distance places it directly within the star's habitable zone, the theoretical region where temperatures should be suitable for liquid water to exist on a rocky world if one happened to be orbiting there instead. To be completely clear about what that actually means, this is the detail that gets flattened or exaggerated in a lot of coverage of this story. A Saturn-like gas giant cannot itself support life the way a rocky, Earth-like planet could. It has no solid surface, no oceans, nothing resembling the kind of environment life as we understand it needs to take hold. But its presence, sitting comfortably within the habitable zone of a genuinely sun-like star, matters enormously for a different reason. It would be the closest confirmed example ever found of a giant planet occupying exactly the kind of orbital real estate where a rocky, potentially habitable world could theoretically exist as well, whether alongside this gas giant or in some other configuration within the same system that hasn't yet been detected. There's another wrinkle in this story that deserves real attention because it's the kind of detail that separates careful science from breathless headlines. When researchers compared the exact position of the object detected by Webb in 2024 against the earlier 2019 detection from the Very Large Telescope, the 2 positions didn't line up perfectly the way you'd expect if you were simply watching a single planet slowly orbit its star along a smooth, predictable path over those 5 years. The discrepancy has left the door open to some genuinely important alternative explanations that responsible scientists are still actively working through. One possibility is that the object really is a single planet, and its orbit is complicated enough, likely disturbed by the gravitational tug of Alpha Centauri b, its stellar sibling, and one of the closest actual stellar neighbors any exoplanet host in the galaxy has to contend with, that its position simply doesn't match a simple, clean orbital prediction. Another possibility, one astronomers take entirely seriously, is that what's being detected isn't a single, discrete planet at all, but rather a clump or concentration of dust and debris orbiting within the system, something more like a dense patch within an asteroid belt or debris disk than an actual solid planetary body. And a third, more mundane possibility that can never be fully ruled out with any single candidate like this is that one or both of the original detections are picking up nothing more than background noise or an unrelated object that has nothing to do with Alpha Centauri A at all. This is exactly why the story doesn't end with the August 2025 announcement, and exactly why the most interesting chapter of this whole mystery is still ahead of us rather than behind us. Researchers Bakeman and Aniket Sanghi, another lead author on the Webb observations, have said that if the 2019 and 2024 detections really do represent the same physical object, Webb should get another excellent opportunity to observe it again in August of 2026. The team has already said they hope to secure additional telescope time specifically to make that follow-up attempt. Think about the stakes riding on that single future observation. If Webb points back at Alpha Centauri A in the coming weeks and finds the object sitting exactly where updated orbital models predict it should be, having moved along an orbit consistent with everything scientists already understand about gravity and planetary motion, that would be an enormously powerful piece of confirming evidence, likely enough to finally upgrade this object from tantalizing candidate to genuinely confirmed exoplanet. If Webb looks and finds nothing there at all, or finds something in a position that simply doesn't fit any reasonable orbital explanation, that would be a serious blow to the planet hypothesis, and researchers would need to seriously reconsider whether they've actually been chasing background noise, an unrelated object, or a disk of debris, rather than an actual world this entire time. And Webb isn't going to be working on this problem alone for much longer either. NASA's next major astrophysical observatory, the Nancy Grace Roman Space Telescope, is scheduled to launch by May of 2027, with some planning documents suggesting a launch could potentially happen as early as the fall of 2026. Roman carries a much smaller primary mirror than Webb does, meaning it can't gather nearly as much raw starlight, but it comes equipped with a coronagraph instrument specifically engineered to be even more capable than Webb's at blocking out a star's glare and isolating extremely faint objects sitting close by. Technology built with exactly this kind of nearby, bright star-planet search in mind. Once Roman comes online, it's expected to attempt its own independent look at the Alpha Centauri system, adding yet another completely separate observatory, using yet another distinct detection method to the ongoing effort to finally settle whether this candidate world is real. Kevin Wagner, the astronomer who made that very first faint detection back in 2019, has described the broader implications of where this research could eventually lead in genuinely striking terms, calling it one of the most exciting results in astronomy of the entire decade, if it holds up under further scrutiny. That's not hype for the sake of a headline. It reflects something astronomers have wanted for decades: real, physical, high-quality data on a planetary system belonging to a star nearly identical to our own sun, sitting close enough that future telescopes, potentially even future spacecraft, could realistically study it in detail that would be utterly impossible for almost any other exoplanet system in the galaxy, most of which sit hundreds or thousands of light years beyond our reach. If Alpha Centauri A really does host a planet in its habitable zone, this system instantly becomes the single most valuable natural laboratory anywhere in the universe for understanding whether solar systems like our own, built around sun-like stars, commonly host worlds sitting at exactly the right distance for the ingredients of life as we understand it. So where does the genuine tension in this story actually sit? If it isn't a completed discovery yet, and it isn't proof of alien life either, it sits precisely in that unresolved space between a strong hint and a settled fact, in a system that happens to be humanity's closest possible stepping stone toward finally answering one of its oldest questions. Every telescope that has ever pointed at Alpha Centauri A across these past several years has come back with something. Never quite enough to declare victory, never quite nothing either. Just enough consistent overlapping signal from independent instruments to keep serious scientists coming back for one more look, one more careful observation, one more attempt to catch this object sitting exactly where the physics says it should be. That is precisely the position we're in right now, in the middle of the summer of 2026, waiting on a telescope currently orbiting nearly 1 million miles from Earth to turn its mirrors back toward our very nearest stellar neighbors and tell us, once and for all, whether the faint point of light astronomers first caught sight of back in 2024 was really a planet all along, quietly circling a sun almost exactly like our own, closer to Earth than any other confirmed world of its kind has ever been found. Here's roughly 2,000 more words, continuing directly from where the last script cut off, and building out the full mystery with fresh detail on the orbital modeling, the historical false alarm this discovery echoes, and what comes next. Caltech PhD student Aniket Sanghi, co-first author on the 2 scientific papers describing this entire saga, summed up the moment perfectly. We are faced with the case of a disappearing planet. It's a strange thing to hear from a professional astronomer, the kind of line that sounds more at home in a detective novel than a peer-reviewed astrophysics journal. But that's genuinely how the team approached what happened next. Rather than treating the non-detections as a dead end, Sanghi explained exactly what his team did with the mystery. To investigate this mystery, we used computer models to simulate millions of potential orbits, incorporating the knowledge gained when we saw the planet, as well as when we did not. Millions of simulated orbital paths, each one tested against 3 hard pieces of evidence: the object appearing in August 2024, the object failing to appear in February 2025, and the object failing to appear again in April 2025. What came out of that massive simulation effort actually solved the mystery, rather than deepening it. The team found that a full 52% of all the orbital paths still consistent with the original detection would naturally place the planet too close to its glaring host star to be visible during exactly the months Webb went looking a second and third time. As Sanghi put it plainly, we found that in half of the possible orbits simulated, the planet moved too close to the star and wouldn't have been visible to Webb in both February and April 2025. In other words, the planet likely never vanished at all. It simply swung along its elliptical path into a position where Alpha Centauri A's own overwhelming glare drowned it out completely, the same basic problem that makes direct planet imaging so brutally difficult in the first place, just now playing out in real time across a single object's actual orbit. The planet wasn't a ghost. It was hiding in plain sight, tucked directly behind its own star's blinding light from Webb's specific vantage point. The technical difficulty of even attempting this observation in the first place is worth appreciating on its own because it explains why nobody managed to pull this off sooner despite Alpha Centauri being humanity's literal next-door neighbor in cosmic terms. Charles Beichmann of NASA's Jet Propulsion Laboratory, describing the challenge involved, called these incredibly challenging observations to make. explaining that Alpha Centauri's stars are bright, close, and move across the sky quickly. That combination, brightness and rapid, apparent motion, is a nightmare for the kind of painstaking, carefully repeated imaging normally used to hunt for faint planets. Bateman noted that his team's operations staff had to come up with a custom observing sequence just for this target, a bespoke observational strategy built from scratch, specifically because no existing method was quite suited to Alpha Centauri's unusual combination of proximity and stellar brilliance. To pull it off, the team used Webb's Miri coronagraph, essentially an artificial eclipse machine, physically masking Alpha Centauri A's overwhelming light, while also masking out interference from its close binary partner, Alpha Centauri B, sitting uncomfortably nearby in the same tiny patch of sky. What emerged from that painstaking process was a single faint point source, formally designated S1, a dot of light roughly 10,000 times fainter than the star it was found near, teased out from behind residual scattered starlight that still leaks around even the best chronographic mask. There's real historical precedent for exactly this kind of now you see it, now you don't behavior in exoplanet science, and it's a genuinely reassuring parallel rather than a red flag. Decades ago, in the early 2000s, astronomers ran into an almost identical situation with a planet orbiting a star called Beta Pictoris. That planet also disappeared from view for a stretch of observations, only to swing back into a visible position later, exactly as its real physical orbit predicted it eventually would. Bateman's team is hoping for the same kind of second act here, and the orbital math gives them a specific, calculable window to look forward to, because researchers ran their simulations incorporating not just the two Webb non-detections, but also the original, tentative 2019 sighting made by the European Southern Observatory's Very Large Telescope using its NEAR experiment. They were able to calculate roughly when this elusive planet's orbit should carry it back out from behind its own star's glare, into a position where Webb could plausibly spot it again. That window points toward August of 2026, and researchers have already said they intend to seek fresh observing time specifically to make that attempt, treating this coming return appearance as the real, decisive test of whether S1 is a genuine planet or an extraordinarily persistent coincidence. It's worth being honest about exactly how tentative this discovery still is, because that caution is baked directly into the researchers' own language. This candidate object has not yet been formally confirmed as a planet. What astronomers have is a repeatedly consistent signal, first glimpsed by ground-based telescopes in 2019, then captured again by the most powerful space telescope ever built in 2024. Its absence in two subsequent observations fully explainable by ordinary orbital mechanics, rather than by the object simply not existing. Sanghi himself was careful to frame the stakes correctly. If confirmed, the potential planet seen in the Webb image of Alpha Centauri A would mark a new milestone for exoplanet imaging efforts. Of all the directly imaged planets, this would be the closest to its star seen so far. It's also the most similar in temperature and age to the giant planets in our solar system, and nearest to our home, Earth. That's an extraordinary trifecta of superlatives for a single object. Closest in, directly imaged exoplanet, closest overall confirmed giant planet system to Earth, and one of the closest analogs we've found to the actual gas giants sitting in our own solar system's backyard. And then Sanghi added the observation that gives this whole story its genuinely unsettling edge, the part that makes terrifying feel less like clickbait exaggeration and more like an honest description of how deeply this challenges basic planetary science. Its very existence in a system of two closely separated stars would challenge our understanding of how planets form, survive, and evolve in chaotic environments. Sit with that for a second. Alpha Centauri A and Alpha Centauri B aren't distant, loosely associated stars sharing a vague corner of the galaxy. They're a genuine binary pair, locked together in a tight, gravitationally chaotic dance, close enough to each other that their mutual gravitational tug-of-war should, according to a great deal of existing planetary formation theory, make it extraordinarily difficult for stable planetary orbits to ever form and survive in the first place. Every time Alpha Centauri B swings through its portion of that binary orbit, its gravity reaches into Alpha Centauri A's planetary system and yanks on anything orbiting there, a repeated gravitational disruption that most models predict should scatter, destabilize, or outright eject planets over long enough timescales. If a genuine gas giant really has been quietly orbiting inside Alpha Centauri A's habitable zone this entire time, surviving that constant gravitational harassment from its stellar neighbor for billions of years, it means planet formation itself is considerably tougher and more resilient than current theory comfortably accounts for, which is exactly the kind of foundational challenge that keeps astrophysicists up at night, in the genuinely productive, science-advancing sense of that phrase. This isn't even the first time a claimed planet around this exact star system has stirred up major excitement. only to run into serious trouble later, and that history is worth knowing before getting too attached to any single headline. Back in 2012, an entirely different team announced the detection of a planet they called Alpha Centauri BB, orbiting the system's other sun-like star using a completely different technique, the radial velocity method, which detects the tiny gravitational wobble a planet induces in its host star rather than photographing the planet directly. That announcement made global headlines at the time, hailed as the nearest exoplanet ever found. Years of additional scrutiny and reanalysis eventually concluded the supposed signal was almost certainly an artifact of the telescope's own instrumental noise and observational patterns, rather than a genuine planet at all, and the claim was quietly, thoroughly retracted from the scientific literature. That history is exactly why the current research team has been so careful, so methodical, and so transparent about the uncertainty still surrounding S1, running exhaustive statistical checks specifically to rule out the kind of instrumental artifact that doomed the 2012 claim, and explicitly stating in their own published papers that it has not yet been possible to fully exclude alternate explanations, including the formal possibility that S1 could still be an unusual dust structure rather than a solid planet, something researchers describe as potentially consistent with a dense zodiacal dust disk rather than a genuine world. Should this candidate eventually be confirmed, the implications stretch well beyond simply adding one more entry to the growing catalog of nearly 6,000 known exoplanets. Saying he described exactly what's at stake. This would become a touchstone object for exoplanet science, with multiple opportunities for detailed characterization by Webb and other observatories. Being close enough to study and genuinely exceptional, detail is precisely what makes proximity so valuable in this field. A giant planet found orbiting a star thousands of light years away can, at best, be studied as a handful of pixels and a spectrum squeezed out through heroic technical effort. A planet orbiting 4 light years away, practically adjacent to our own solar system on any galactic scale, becomes something astronomers can return to again and again, refining its orbit, studying its atmosphere, searching its system for smaller rocky companions that might be hiding nearby, all using an ever-improving lineup of instruments. NASA's own Nancy Grace Roman Space Telescope, scheduled to launch in the near future, is specifically being built with a coronagraph engineered for exactly this kind of nearby star-planet hunting, and researchers have already flagged Alpha Centauri as one of the very first systems they intend to point it toward, adding yet another powerful set of eyes to the ongoing search for whatever, exactly, is quietly orbiting our sun's nearest sibling star. So where does that leave the story right now, sitting at the point where we are today? A faint, repeatedly detected signal, glimpsed once by ground-based optics in 2019, caught again by the most advanced space telescope ever constructed in 2024, then twice absent from view in early 2025 for reasons that orbital mechanics alone can fully explain, sitting inside the habitable zone of the nearest sun-like star to Earth, in a system so gravitationally hostile to stable planets that its mere existence, if finally confirmed, would force astronomers to rewrite parts of how they think planets survive at all. The next real test comes in August of 2026, when the same orbital calculations that explain the planet's disappearance predict it should swing back into a position where Webb can see it again. Whether that observation finally confirms a genuine world quietly circling our nearest stellar neighbor, or instead reveals nothing more than scattered dust and a very convincing coincidence, remains one of the most closely watched open questions in all of modern astronomy, playing out just 4 light years from the place you're sitting right now.